And hello and welcome everyone. This is Peter Robinson here. Welcome to the Ethereum Engineering Group meetup. Today, Raghavendra and myself are going to give a talk about code Merklization. Raghavendra, would you like to introduce yourself?
Yes, thanks, Peter. I am Raghavendra. I joined Consensus in October last year. So I've been working on atomic cross-chain and then now on code Merklization and more generally witness compression. Yes, thank you.
Yeah, and thank you, Raghavendra. And so I'm Peter. I've been at Consensus for 3 years and been in the blockchain space for 2 or 3 years before that, off and on. Like Raghavendra, working on cross-chain and code Merklization. So let's get the slides up. And of course, when you search for your slides, you find them hard. Okay, let's minimize that and click present. Okay, so today's talk has been made possible by Zhenyang and Horacio gathering data and giving us some data. And here I will stop my video as well. Yeah, by Zhenyang and Horacio gathering data to feed the analyses that we've done. And Sandra has also helped out. And we've also had Sina from Ethereum Foundation who's reviewed the slides as well and given us some valuable feedback. So we've got a lot to cover today, but the start of it is really explaining stateless. And so the analyses code is available under Apache 2 license at that GitHub repo. The source data, which is essentially all of the Ethereum contracts on mainnet, we'll release that probably next week in a separate GitHub repo. We'll also have the list of transactions. So what we've essentially done is grabbed all of the transactions that have hit mainnet and or at least a big swathe of them. And so we'll also have that data on that website. So then we'll be able to reproduce these results. So just the whole code Merklization is a witness compression technique, and witnesses are needed as part of stateless. So understanding stateless is a good starting point. And so in stateless Ethereum, so that's what's thought about for Ethereum 1.x and then also for 2.0, you've got these semi-stateless nodes, and they hold accounts that they're interested in. And so they could have no state at all, or lots of, or the whole tree. They could be essentially like an archiving node. It really comes down to the configuration of these nodes. And so in this style of architecture, you've got your miners and seeder node, a semi-stateless node that maybe has the full state, and then maybe a partial state semi-stateless node. And so the idea is that say you own the semi-stateless node that is only going to store partial state, you might actually be on 3 different networks to acquire all the states you need. So the first, when you start up, you could use what's called merry-go-round sync. It's a new sync protocol that's been discussed and analyzed. And the idea is it sprays out all of the state tree at a certain snapshot point. And so you could listen to that whole state tree and just capture the parts of the state that you're interested in. Though that would require you to wait, say, 24 or maybe 48 or maybe 72 hours listening to the whole state fly past. An alternative would be maybe you could pay someone to give you the state that you're interested in. So at the moment, we've got gateways such as Infura, and you could imagine those sorts of services could also be state providers as well. And so in parallel with getting the snapshot of state, what you need to do is be getting these witnesses, which are essentially are the delta. And so it's essentially saying, here is the block and all the information you need to verify the block. And part of the output of that will be the update of state. And the update of state would allow you then to keep your piece of state that you're interested in up to date. So for the purposes of this talk, we're going to be talking about the witnesses that are part of this sync protocol of delivering the state, and in particular, just the code. So as part of the whole stateless and witnesses includes the data and the code, but this is just focused on the code itself. And so the code compression has generally been called Code Merklization. So this graph here shows an analysis by Igor and Drigan, who had a look at, for hexary trees, or hexary tries, should I say, the contribution of witnesses if you have for the hashes, the code, the masking and leaf keys, and the leaf values. And as you can see, hashes are big, but code is also very big. So if you could reduce the contribution of code, then that would be massive. And so hence, that's why focusing on reducing the code contribution to witness size is important. So this diagram here, or this slide here, shows the overall state tree. And so you can think you've got a block header in Ethereum, and one of the things it's got in it is a state root. And the Ethereum clients keep a Merkle Patricia trie of all the accounts. So you can think you've got those 160-bit accounts. And so that is an address into this overall trie. And then the leaves are the account state. And the account state stores some things. And one of the things it stores is the storage root. And then under that, you've got all of these storage values that you keep. So when we're talking about Merkelizing code, we're really saying, well, let's replace this code hash, which points to some code, represents some code. We're going to change what's below here so that when we want to say, hey, this code was accessed, rather than sending all of the code, we just need to send part of the code. So when we're looking at analyzing all of that code and how, what's out there and how we can best approach it, one of the things that we were looking at and thinking about was, well, what code is actually out there? And this graph here shows 3 types of contracts. And so the one type of contract is what I'm calling new Solidity. But essentially the Solidity code typically starts by setting up a free memory pointer. And so it has 5 or 6 bytes that are very similar all across those contracts. And it's a standard starting point for all those contracts. So you can detect what I'm calling a new Solidity by looking at that. Older Solidity contracts start with a slightly different pattern. And again, you can detect that. So I didn't have time to check, but I'm almost 100% certain that if you compile with version about 5 and beyond, you end up with new Solidity style, and maybe 5 and before, it's old Solidity style. And as the other alternative, of course, is something that isn't Solidity, and that's shown in blue. So you've got the orangey reddy color is new, and green is old, and blue is other. So you can imagine, given it's just bytes, and so byte code, there's no reason why anyone couldn't write a contract, even say in assembler, that could have the same starting point bytes as a Solidity contract. So this analysis would hence classify it as Solidity, even though it wasn't. That said, having a look at this gives us a bit of a gut feel for what the proportion of Solidity code versus other code. And as you can see, Solidity is by far the most prevalent language out there. And though a lot of contracts were written using the older language, there's also, I mean, the older byte code, there's still some that, there's a lot new byte code that's come about. So analyzing based purely on Solidity would hit a lot of the contracts. So this is about when the contracts were deployed. This next graph is talking about when the contracts were last accessed. And it shows a similar but different pattern, showing that even older contracts are still accessed. So some of these older contracts are things like CryptoKitties, for instance, and they're still accessed, and you can see that there's still usage. So again, being able to process older Solidity contracts as well as newer Solidity contracts would be important. And this graph here is a scatter plot based on last accessed. And Sandra, given you produced this, do you want to have a quickly talk to this slide?
Sure, Peter. So that was instead of using like a bar plot, I thought it would be interesting just to view them as a scatter plot, so the individual observations. So it's a little bit hard to see because a lot of it is overlaying on each other, but you can see from towards the right, you can see little blue dots in between there, and it was giving the, I think this was actually to do with the number or the size of the block, the size of the contracts, perhaps, rather than last accessed. I'm not 100% sure. No, that is, yeah, you're quite correct. It is the deployed, but yeah, so it was actually just trying to get the individual points on the graph. And the interesting thing there, I think, was to see that whole shift towards the new Solidity as well. But you can see behind that, because unfortunately it's not see-through, but you can see through some of those gaps that there is still a lot of underlying sort of older Solidity being accessed, which was more, which was clearer, I suppose, in the other, in the previous graph. Yeah.
Yes, thank you. And you reminded me, and I have mislabeled this slide, so sorry everyone. This is supposed to be about contract size, and you reminded me. So the big thing that this was showing was, so down the bottom is when the contract was deployed, and along the side is the size of the contract. So there's a hard limit of 24 kilobytes. And what this is showing is that the larger contracts are becoming far more prevalent. I think that that's really what you can take from this, especially written in the more recent versions of Solidity. But generally, newer contracts are bigger. Yeah. Okay, example code. So to try and make all of the talk that we're going to go through a bit more tangible, we're going to have an example contract. And so the ERC20 contract, so the contract that is used for ERC20 tokens, is really just an API. And so any contract that complies with the API is an ERC20 contract of some sort. So the Open Zeppelin project, they've got an implementation, and their implementations are used all over the place because they have been vetted and are deemed to be very good. So that the version of the ERC20 contract that I'm using to demonstrate. So, and just to give you a feel for how many ERC20 contracts there are 269,000 of them, which is a lot of contracts. So in the ERC20 contract by the Open Zeppelin project, they've got this list of functions, of which the ones that I'm showing here that are in the darker font are the ones that are actually in the ERC20 interface, and the others are extra functions that they've added in. And so when you're thinking of a contract, you've got to remember we're in bytecode, and so you have this sort of this sort of code starting at a certain program counter, and going to the end of it. And so trying to visualize a whole contract, and so with the top left being program counter 0 and going across the screen to program counter 320, and then going down 0, 320, 640, etc. And so assume that this is the overall ERC20 contract. So then if you have the name function executed, then it will also, all execution of contracts starts at program counter 0. And it, as per the talk that we did last fortnight, you do a bit of jumping around and then comparing against the name of the function, so essentially the function selector, and then you execute code and you jump around the code. And so where the X's are code that is accessible from the name function. So the first parts are just getting to the name function, and then the rest of it is the name function itself. And so that's the name function. And the approve function, as you can see, different set of code that it executes. And then total supply, it's only very small. Whereas transfer from uses a lot more code. And so as you can see, for these different functions, they're located in different parts of the contract, as you would expect. Where transfer from is the largest. Yeah. At the end of a contract, you have metadata or auxiliary data. And so this is information which allows you to have the hash of the source code and pointing to it in IPFS or Swarm. And also the Solidity version or compiler version, and or the name of the compiler, and some other metadata if you want to. So that's at the end of the code. So another thing to think about is that as well as the functions and the metadata, you've also got some extra tiny bits of code. And so you've got, so in this contract, none of the functions were payable, and hence if the transaction comes in and the value isn't 0, that's caught right at the start and it'll fail. There's also, because you've got more than a certain number of functions, the function table is split. And so it essentially says, is the function above this, jump to a second part. And so what that means is at the end of the first part, there's a jump for if you haven't hit a known function selector. And then right at the end there, you've got the revert if no function selector was found. And this is essentially the case for where you would get to if there was a fallback function. Okay, so you can see that how the code's laid out. So now let's talk about methodologies. And so overall, what we want to do is look at creating some sort of new data structure for code storage that allows less code to be sent to validating nodes as part of a code witness. And that's what it really comes down to. How can you send less than the whole contract? And so, for instance, maybe the code can be stored in a Merkle-Patricia trie, with the leaves of the tribe being the code. And so in this, so the thing to think about is that depending on the methodology, what ends up in those leaves is going to be different. And the keys, what the keys actually represent, will be different too. So that will be methodology dependent. So when you're thinking about code Merkleization techniques, you've got to think about the extremes. And so one extreme would be to send all of the code in a contract. So send the whole contract. And so in other words, don't change anything. Don't Merkleize the code. Another extreme, the other bound would be, well, let's work out exactly which bytes are executed and somehow or other prove that, that those bytes belong to the contract. And I'm not sure how you would do that. I know, so Sina was saying that he was thinking that somehow or other you might be able to use a zero knowledge proof to do that. Yeah, it's an open question as, is there a way of doing that? And the amount of hashing, hashes and the amount of structure required for a methodology like that could be considerable, but maybe it wouldn't be. So it's, but that would be the ideal though, if you could just send the bytes that are executed. So the issues affecting witness size is the amount of unneeded code bytes that are included. So assuming that you can't perfectly just send the bytes that are executed and you need to send bytes that you've got in a Merkle-Patricia trie, you're probably going to have extra bytes that you don't really need. So they'll have to be sent anyway though, because you'll be trying to hash that data to produce something that hashes up to the root hash for the code. So you've also got to send the hashes and the structure, the proof. Sometimes you might send, some of the methodologies could end up allowing you to send duplicate code bytes. So the same code bytes twice, which would be bad. That would be in particular due to maybe you could have deployed the same contract to 2 different addresses. And so some of these ERC20 contracts, for instance, so you've got the same source code compiled with the same compiler version. So you've got exactly the same code, but it might be deployed in 3,000 different places. So if the code Merkleization approach can't be actual code aware and is only address aware, then you would end up sending duplicate code. And so another thing to think about is hexary or binary trie. So binary tries are going to be more efficient. The amount of efficiency is going to depend on the methodology. So this is a gut feel of mine, and we really do need to do the analysis on it. But my gut feel is that a multi-Merkle proof is not going to be as efficient as when you're going from hexary to binary as a single Merkle proof, simply because of the leaves involved. Okay, I'll pass it over to Raghavendra, and so I'll stop sharing. And Raghavendra, do you want to share your slides?
Yes, yes, please.
All right, over to you, Raghavendra.
Okay. Second. Yeah. Are you able to see the slides now?
No, yes.
Yes, okay.
Yeah.
So, yeah, thanks. Yeah, thanks, Peter. So I'll now explain some of the basic ideas for code Merkleization, or the way to, or the alternatives to the extreme approach where we send the entire code. So especially I'll explain 3 approaches: strict fixed size, and jump test approach. Let me start with the strict fixed size. Yeah, the idea here is simple. Given a parameter t, which actually means the threshold number of bytes, we chop the code into pieces, each of size t bytes, exactly t bytes. So I think from previous previous meetup talk, we know that EVM opcodes actually might span more than a byte, especially if you look at the push instruction. Then you have push opcode followed by the data that needs to be pushed. It might so happen that a chunk might cut an instruction in half, but we'll stick to that the chunk is actually a fixed size. But in addition, in the chunk, we need an indicator saying that the offset for the first instruction inside the chunk. Okay. So essentially, the strict fixed size analysis gives a key value set of pairs, where keys are the start addresses and the values are a tuple offset for the first instruction and the code chunk. Okay. Hopefully this is clear. Now let's look at an example. Look at an example of ERC20 transfer function. As Peter showed, the XS actually represents. Yeah, the X is actually the executed byte codes for the transfer function, and if we chop the code for with 128 bytes as each chunk size, then we'll have this picture. Essentially, we have 21 chunks, and this function, the transfer function, actually utilizes only 13 chunks of them. It's pertinent here to see that we'll have to include the number, many unneeded byte codes, in fact. Okay. So we have these 21 chunks, and if we can represent this in a Merkle-Patricia trie, especially the hexary Merkle-Patricia trie. And this would be the representation of it. We have a branch node in the top, that's the root. In a hexary trie, each branch node actually has 16 children, indexed from 0 to 15. So in the top, we have only 2 children. They are again branch nodes. And in the next level branch node here, we have 16 children. So all pointing to the 16 chunks here, and you have 17, 18, 19, 20, 21. So totally 21 chunks of the ERC20 contract. This is the Merkle trie for the ERC20 contract. Now suppose there is a transaction which executes ERC20.transfer, then it needs to send the code responsible for executing this transaction. And the code responsible for executing this transaction happens to be only on these yellow chunks or yellow boxes. Okay. So we are not sending the entire ERC20 contract code now for a validator to validate. We are actually sending only these yellow boxes, which has the ERC20 transfers code. But in order to ensure that the sender is not tampering with this code, we need to have a proof. Those proofs are nothing but these hash nodes. So whatever the chunk we have here, we take a hash of it, use that hash, and these green nodes are the hashes. So along with the yellow nodes, that is the required code segments, we also have to send the green boxes, which are the hash nodes. Upon receiving these things, the receiver can actually hash these code chunks of the yellow boxes and finally calculate their hashes. And using the hashes that has been given, the green boxes, he can calculate the branch node hash, and eventually he can calculate the root hash, or that is the Merkle root. And the receiver is supposed to store the Merkle root and verify whether this matches or not. So if it matches, then the receiver is sure that the code chunks that he has been given with is not tampered. So the integrity of the code is ensured. So this is how the multi-proof is used as an integrity proof. The thing to note here is these hash nodes, and these hash nodes are the burden, right? They don't serve for a honest node. They don't serve any purpose in terms of executing the transfer. So in terms of evaluating different code Merklization strategies, we'll have to look at these number of hash nodes for each transaction. That will give us the proof burden. Okay. Yeah. So as Peter said, the one parameter was because we are chunking the code and we are sending the whole chunks, we will be sending some unneeded data as well. For example, these dots are unneeded here, these dots are unneeded here, and this chunk has less code that gets executed, but there are lots of unnecessary code. A natural approach to think is to vary this threshold size. Maybe 64 bytes would matter in this dimension, saying that the amount of unnecessary code that needs to be sent will be very less. So one can experiment with let's say 64 bytes chunking. This is the same approach. Instead of 128 bytes, I'm chopping the code with 64 bytes. In this case, we'll have 41 chunks, and the ERC20.transfer function will occupy 19 chunks of them. In terms of Merkle Patricia trie, we'll have such a structure. We'll have 3 groups, in fact, in the leaves. And if you look at the multi-proof, then we'll have, as I said, 19 leaf nodes. But remember that these leaf nodes are not exactly equivalent to the previous leaf nodes in terms of size. These are 64 bytes. Previously it was 128 bytes. So these are half in the size. And the number of hash nodes we require has jumped to 22. Previously it was only 18. It was 8. So though chunking with a smaller threshold decreases the amount of unnecessary code that needs to be sent, but it does increase the burden of proof in terms of number of hash nodes. So threshold is important. So experimenting, evaluating across all the blocks for all the transactions for different thresholds and determining the optimal threshold will be the way. So a slight variant of this approach is a fixed size chunking. That was a strict size chunking, where we were even, we did not hesitate to chop an instruction in half. This variant actually kind of wraps the instruction into the chunk fully. So this is the key point, include the last operation fully in the chunk. So the key value pair is simple, start address and chunk. I did check for the ERC20 transfer. It happens to be the same way as the fixed size has behaved. So no changes in terms of the number of hash nodes or the structure of the multi-proof. So another popular and simple methodology that is being discussed in the stateless Ethereum community is jump test approach. What is jump test? Jump test actually is an opcode which indicates the position in the code where jump instruction can jump to. For example, the jump test instruction here is at PC 0xF, right? And if you look at this instruction, push 10F and jump I. So this instruction is actually causing the control jump to this opcode, provided that because the stack top is 0xF, will jump to F, provided that the previous stack top or the top -1 stack is 0. So this is a valid jump destination. So jumps cannot allow the control to jump anywhere else. It has to be on a jump test instruction. Okay, so this is one of the structural artifact of EVM opcode. This approach of code Merklization also is parameterized with a threshold T. The first point here is to chop the code in terms of basic blocks, or just to have the blocks of code where there is no jump. It's just no jump instruction sequence, straight line code. And then we stitch these basic blocks into a chunk till we reach a minimum size, which is till we reach a size greater than or equal to T. Then again, this can be thought of as a key value store, where key is the start address of each of the chunk, and the actual chunk is the value. Again, let's see the jump test approach with the threshold 128 bytes for ERC20 transfer. In this approach, we'll have 18 chunks, and for this method transfer, we need only 13 of them. So in terms of Merkle trie, this is the Merkle trie for the jump test approach for the ERC20 contract. You can see that there are 16 nodes here on one branch and 2 nodes, that is 18 nodes totally on the second branch. And for a transaction executing a transfer ERC20 transfer method, we would need to send the, I think this is typo here. Yeah, it's 13 chunks. So this leaf data node should be 13 here, and this should be 5. Okay, so the amount of leaf data nodes, each of size at least 128 bytes. We need to send 11 nodes, and we need to send the proof of 5 hash nodes. That's typo here, 5 and 13. One interesting thing to note here is in this group, the transfer method is not executing any code from these leaf nodes, the leaf nodes of this branch. So in that case, we don't have to individually hash it and send it across. We can take the cumulative hash and send the hash of the branch. That's enough for to ensure the integrity, because given the leaf nodes and these hashes, we can compute the hash of this branch. Using this hash, we can compute the Merkle root. So this is one of the ways in which multi-proof provides some kind of proof size optimization. Okay, let's look at the scenario where we do the same jump test chunking, but this time we use the threshold of 64 bytes. Okay, in this case, we'll have 32 chunks, and the transfer method uses 14 of them. In terms of pictorially, 32 chunks has a very uniform trie structure, and the transfer method leaves us that the sender of this transaction needs to include 14 leaf nodes and 18 hash nodes. Yep. So So that's basically the basic approaches. In terms of just concluding this part, we saw 4 or 6 approaches, but in terms of fixed and strict fixed, they behaved the same for the ERC20 transfer. So for a fixed size chunking analysis with 128 bytes threshold, we had the overhead of 8 hashes. Hashes are typically 32 bytes. So it's like 18 to 32 bytes of overhead. For a fixed 64 bytes, we had 22. And the jump test approach, with the jump test approach, we had just 6 hashes for 128 bytes and 18 hashes for the 64 bytes. It's interesting to see the tussle between the amount of unnecessary code with respect to and the amount of hashes that needs to be sent. So this is just a use case for this analysis. A rigorous analysis with rigorous evaluation with multiple methods will be shown in the later section. Okay, that's all from my side. Any questions or thoughts? If not, I'll hand it over to Peter.
Okay, thank you, Raghavendra. And I better progress through the slides. I should have all right, so the next approach is the function selector approach. And the function selector approach will work for Solidity and any other language which obeys the Ethereum application binary interface. And so the overall idea is that have a Merkle-Patricia trie, and the leaves of the trie represent functions. And so you could say say for that transfer function, you could have all of the accessible code you can get to from the transfer function and have that as a leaf of the trie. And so the thought is that only having to do a single Merkle proof might actually be smaller than a multi-Merkle proof. So that's a thought. So you're only going to have to send one Merkle proof because you're only sending one leaf. And so the thought is that should be smaller, maybe, but I guess we need to prove that out. And in particular, though, you should be probably on average sending less code. Though, as you'll see later, there are circumstances when other methodologies may end up sending less unneeded code. And so a function selector is a 4-byte value, which is the truncated message digest of the function name and the parameters. So essentially the function signature. And so if you search the code, so on bytecode for things that look like push 4 and then a number, and then EQ, push 2, and then an address, and then jump I, that is invariably a jump to a function. And especially if it's right at the start of the code between the call data load and the first return, stop, revert, or invalid, or some way of terminating the contract. So you need to use call data load, or a contract uses call data load to load up the function selector, and then it does the comparisons, and then invariably there'll be a revert at the end of it or a stop, indicating that there's a fallback function or there isn't a fallback function, and there's going to throw a revert. So that's the methodology of finding the list of functions. And once you've found the functions and the function entry points, then you do a static analysis to work out all of the accessible parts of code. And then you create a list of code segments or code blocks used by a function. And then if there is only 4 bytes or fewer than 4 bytes between segments, then you combine those segments together. And the rationale for that is that for representing each function, or each segment, you need to have a start, offset, and length, and each of those are 2 bytes long. So if you're going to have only 4 bytes or less, then you might as well just have a single contiguous segment rather than having 2 segments with 2 sets of lengths and starts. So hence, for something like a ERC20 transfer function, you're just going to send the bytes you need to send. And there is a little dot there at just there, which shouldn't be there. So I should fix my slide at some point. You will notice though, there's a dot here. I don't know if you can see my cursor, but right at the start of the code, there's a dot between 2 sets of X's. And what that's all about is that's if there was call value, then fail and do a revert. And so because that little piece of code is 4 bytes or less, it gets brought along with this because you combine 2 segments into one. And another thing to note is that you have to worry about executable code, but you also have to worry about stuff from code copy, so essentially data. So rather than loading something from storage, if you've got a constant, you might load it from the code itself. And so that can often be used for loading up error messages for reverts. So the idea is that once you've got the data, you've got the chunks, you then put the code itself and the metadata and store it as a Merkle-Patricia trie. And the keys for each of the leaves is the function selector. And you'd need 2 extra special pseudo function selectors or keys. And one is for all of the code, and one is for the fallback function. So the thought is that if invalid function selector is used, so essentially a transaction with an invalid function selector, then the best way to handle that is just to use all of code. And if there's no function selector, so if there's no data at all sent to the transaction, then just use the fallback function leaf node. So each leaf contains 2 bytes, which is the number of blocks. And then for each block, the program counter start of the block and the length of the block. And that's then at the end of it all, you've got all of the pieces of code that are needed, the code segments. So when, though that the code would be there logically, the software may choose not to physically have the code there. It might just have the code in one contiguous block somewhere. That's implementation specific, but the idea is the code would be represented by the hash of that leaf node. So when you're sending a witness for the same contract or or even if you've got it deployed at 2 different addresses, you should only send 1 copy of each code chunk that you need to, so you don't send duplicate code. So there are a few issues with this technique. So if a code doesn't support to the ABI, that is, it doesn't have function selectors, then it can't be processed. And unfortunately, I didn't put the percentage there for that, but I believe that is in the order of about 5 to 10%. So that's one issue. Another issue is that there is code out there that's got invalid jump destinations. And as well, there are some code copies that use dynamic parameters, so it's hard to work out what it's actually copying. There are dynamic jumps as well. And some of the contracts, the processing has failed, and we need to investigate exactly what's happened. But for some reason or other, the static analysis hasn't worked on them. And I think I know what the issue is, but yeah. And so to improve things for the jump tests, we need to really review it. And I think that some of the jumping to an invalid jump destination is actually a form of doing a revert. So I think that some people, maybe they've put some code in and they're doing that just to fail, but maybe it was a bug in the compiler. I'm not sure. So I've got to analyze to be 100% certain that all those invalid jump dests really are invalid, and then try and understand whether somehow or other the rest of the code could be used. And it'd be interesting to see.
I think you posted an example of that before a couple of weeks ago, and yeah, it looked like there was a code optimization that saves like 1 or 2 bytes by by reverting via a fake jump destination.
Yeah, yeah. So yeah, so maybe that's what's being done. So if that's what's being done, then maybe it's an okay thing to just say, all right, we'll Merklize those, we'll process those and just ignore the fact that there's an invalid jump dest and treat it like a revert, maybe. Yeah, and thank you for that, Sly. There's also some code copy with dynamic values, as I said. So at the moment, the constant propagation isn't as good as it could be. So constant propagation is a static code analysis technique where even though you've got values going via variables, if you can work out that it was a constant, then maybe you can work out that it, say it wasn't a function parameter or something. Yeah, so maybe those dynamic copies aren't really dynamic. Similar for the dynamic jumps, maybe they're not really dynamic jumps. If so maybe better constant propagation would help to work that out. And the failed process, some of them are certainly really, really complicated recursive functions and interrelated recursive functions. And so though I've said that there are some that haven't been able to be processed, and my hunch is that they're recursive functions, it would be really good to actually write by hand our own Solidity code that breaks the technique and that fails to process. Trying to have something that is not only recursive but have function calls that are interrelated. So one of the things you do when you're doing static code analysis is that you're looking at the stack coming into a function call or into a code path to try and analyze, well, have I seen this stack before? And, should I be able to, just say, right, I already know about this code path execution. And so maybe you could try and manipulate it so the presented stack always looks different to the static code analysis. Yeah. So another issue with this technique, which is not related to anything I've talked about before, but is a much bigger issue or much higher level issue is, so you might remember there was some bytecode that I specified and said, well, this is what it looks like when Solidity does a jump to a function call and checks for a function selector. So if you hard code that analysis into Ethereum clients, then what that means is Ethereum clients, for the first time ever, really start to know about the ABI. So at the moment, Ethereum clients just execute bytecode. They know nothing about the application binary interface. But they would then start to know about the ABI. And if Solidity was changed to have a different way of selecting functions, then that would cause problems for this methodology. That said, I can't see any reason why Solidity would necessarily change, because what it is seems to work, and yeah, so it sounds like an issue, but it may not actually be much of an issue at all. So after all of that evaluation, so how we evaluated the techniques was we collected contracts that had been deployed on mainnet, And so we collected all of them that had been deployed with an externally owned account transaction deploying a contract. And we're in the midst of collecting all of the deploys that have happened due to code. So due to one contract deploying another contract. And so we haven't, at the moment, our data set doesn't include that. It only includes contracts deployed by externally owned accounts. The function selector approach was then used to statically analyze the contracts. And so essentially try and understand, given what these functions, what code can you touch? And then for each of the blocks, so for each block, and we've run it through quite a few different sets of blocks, but for each block that we use to analyze, get all the transactions from the block, and then determine the to address and function selector for the transaction, and making sure that the to address is a valid contract. And then for the strict fixed and jump test approach, assume the code identified by the static analysis is actually the code that's executed. And so it's going to be a bit of an over approximation, but it should be reasonably okay. Another area that we were in the midst of doing but didn't quite get done for this talk was creating the multi-Merkle proof for each block. So the multi-Merkle proofs are block-based, and so what you would do is you gather all of the leaves of code that you need to send, and then do a multi-Merkle proof of that, and then you'll not only include the leaf data, but you'll also include the hashes and any other structure that you've got when you're calculating the witness size. So unfortunately, we didn't get to put that step in. And so this is the graph that we've got. And I can hear you say that, what does it actually mean? What's this mean? And so this is across what, some thousands of blocks. So it's not in the scheme of things, it's only what, 3,400 blocks. So that's not many blocks really. But what it does show you is that the witness size goes up and down quite a lot depending on the block. Independent of methodology you want to use, the witness size varies substantially block to block. Zooming in on just 100 blocks though, you can see the function selector approach yields smaller witness sizes compared to strict and fixed and jump test. And so in fact, the other three, the jump test, fixed and strict, are all around about the same, whereas the function selector is definitively less. Now, this doesn't, as I said, doesn't include the hashes. And my guess is that you're going to need the hashes and is going to be better for the function selector than the others. But maybe I'll end up being wrong and it will be the other way around. So there's also some of the contracts which couldn't be analyzed. So if a contract couldn't be analyzed, say due to dynamic code copies, then the witness for this technique was included as the whole contract. So it'd be interesting to change the analysis to just completely remove those as outliers and not have them, because they would tend to mean that or for all techniques, they're going to end up with pretty much the same or the same witness size for one of those contracts that couldn't have been analyzed. And so, yeah, it'll be interesting to see what that looks like with those out. Of course, something to consider is that if in the long term, the function selector approach couldn't analyze some code and had to send the whole contract, whereas the other methodologies didn't, and they could just send the code, the blocks that are used, then they would end up having a much smaller proof size. So yeah, and another line that would have been really fabulous to have in this graph would have been the total contract summation size for each block. We'll do that next time. So this is another scatter plot, and I think along the, independent of what it says on the side, the axes, I think it's block number across the bottom and witness size across on the y-axis. And what I think this is telling us is that actually, I'm not sure. Sandra, do you want to talk to this slide?
Sure, these were obviously created in a bit of a rush. Yes, I think you're right. That is to do with the sizes. So that was really taking the code sizes from the data set that I had. So I presume it will look something similar to the previous graph, which I quite liked actually. So this was just plotting the code size for the blocks. So we had the different blocks and we had the different chunking, Merklization techniques. So the fixed, the function ID, jump test, and strict witness sizes. And it was plotting the code. It was plotting the size that I had for each of those different methods. So it's, you know, if you look down each of those lines, it's a bit hard to see because it's including so many blocks. Yeah, but I mean, it looks like when you trace some of them back, it appeared to me that some of the function ID witness sizes were actually quite promising. But then with the fixed witness sizes, there were quite a lot just around 0 down the bottom that I noticed. So yeah, it's a bit hard with a scatter plot because everything seems, because you can't really see them on a straight line to exactly compare one to the other. I think it's quite nice to zoom in and look at some bits in more detail.
Yeah, I think so. It's trying to visualize this information, especially as you get to large data sets, gets really confusing. So I think that's maybe another thing we should have in the things to do from here is try and work out how to visualize this better. Yeah. All right. Well, thank you, Sandra. Yeah, thank you. All right. Let's have a look. Let's go forward. Oh, yeah. So another thing to consider with the methodologies, or in particular the function selector methodology, is imagine this code here, where you set up the owner of the contract, and then you call stuff, and if you require that the message sender equals owner, and what's going to happen is you're going to revert if that doesn't happen. And then below there, you can see you've got some state, and if you state variable equals 2, then you do this, otherwise you do that. So you got 2 completely different execution paths. So in the function selector approach, you're going to say, well, from the function stuff, you can access all that code. You can, access the revert in that the require calls, and you can access do this and do that. And so it's going to send you a witness that's going to include all that code. Whereas the other methodologies, if the transaction fails due to the revert, then you're only going to get that piece of code right at the start of the function. And it's going to only go down one of those code paths, do this or do that. And so you're not going to have everything. And so in those instances, you're going to have less code. Now, the thing to think about is how often do you have this sort of logic in a Solidity contract, and how often do you have large amounts of code that are conditional? So you have requires a lot, but then how often do transactions on Ethereum mainnet hit those requires? Normally the requires are there as a safeguard, but normally most transactions go straight through them because otherwise they'll fail. And so people make sure that they don't hit the requires. So I guess that's something that we need to analyze. How often do transactions hit requires and revert? And how often do they run to completion? I don't know that we've got that data yet, and I'm not sure that anyone else does either. So yet another area of inquiry. Yeah. Yeah, so as I said earlier, the static analysis is an over approximation of the code that's executed, so that there would be normally less code. Okay, so over to you, Raghavendra, to talk about the proposed migration strategies. Should you just talk to this slide, or do you want to share your slides?
No, I'm happy with your slides, that's fine.
Okay.
Okay, so the problem, the migration problem is currently the state trie has the account values, where the account values hold a code hash of the code. The migration problem is to change the code hash to the code Merkle root of the code trie. Okay, if we put the entire code on Ethereum mainnet, it's currently around 1.4 gigs, so it's not too hard. It's not too, what can I say? It's not too large. So the one-shot approach says that you make a hard fork, and then you ask every node to maintain the code trie from here on, and have the code trie root in the account value. So, but still some things needs to be worked out. For example, the Xcode copy. Xcode copy normally returns the entire code from a given address. But does that mean here should we return some chunks? If you're returning some chunks, should we include a multi-proof? I don't know. And there's this another instruction called Xcode hash. So it takes an address and returns the hash of the code at that contract address. Now, should this be kept as is, or should we return a Merkle root of the code rather than a code hash? So these questions are still not finalized and still being thought over. So the normal mechanism is to do a hard fork and allow all the nodes to upgrade to a Merkleized structure. Another thought that is being doing rounds is, anyway we have to do hexary state trie and storage trie to binary state trie and storage trie conversion. So maybe code Merklization is best positioned at that conversion time. So it may be better to club all these transitions together as one shot. But it's not, nothing is final here. So these are all being still thought over. Next slide, please. Yeah, so the one-shot approach is that, but people still are thinking about to have a new machinery, which will, or a new process, which will enable a soft and a gradual conversion, or gradual migration. And if this process is finalized and are agreed upon and is efficient, then this can be used for multiple tasks. Code Merklization is one, hexary to binary trie conversion is another, and tomorrow if we find that KCOC is not good enough, we need some other hash function, we can use the same process. Or let's say the polynomial commitments work out to be good, and we want to remove the Merkle trie structure altogether and store polynomial commitments, then also this process can be used. So that means there is incentive to come up with new process. So yeah, but we don't know, we don't have the process yet. So that's all there is, the thoughts. Over to you, Peter.
Thank you. All right, so we've talked about code Merklization, and for people who use mainnet, one of the big things that you'll be asking is, well, what about the pricing? How much is this going to cost? And so how Merkleization or code Merkleization will affect or should affect pricing is really an open question. You know, there is an open debate, and yeah, no, nothing is finalized. So, you know, should deployment cost more than it currently does? Because at the moment, you're just putting an array of bytes and you're, you know, working out the hash of those bytes. And then you're saying, hey, do we have this hash in our key value store for the code yet? And if we don't, then let's just store this code. So now we're talking about even the simple approach is you're Merkleizing it. So you're splitting it up and then creating a Merkle-Patricia trie. But say for the function selector approach, you're doing a static code analysis. And so that could take some substantive amount of time, you know, some order of 10 or tens to hundreds of milliseconds for a large contract. So yeah, should deployment cost more? And another thing that, you know, you've got to think about is, so what about that external code copy? So it's hard to, you know, hard to know how much of the code is going to be used. So how do you do that pricing? So certainly from the function selector approach, you're probably going to end up having to load the whole of the contract. And so how often is external code copy used is another thing to be looked into to understand how important it is. And another thing is that at the moment, there's a hard limit on code size at 24 kilobytes. And that was introduced during the spurious Dragon hard fork and for EIP 170 to try and prevent some attacks. So people are keen for that to be increased. And so should the methodologies allow for this possibility is something to be thought through. Okay, so a lot today I've said, hey, we need to look at this a bit more, and it's very true. There's a lot more evaluation, experiments and analysis is required, really. So we need to evaluate all of the contracts on mainnet, not just the ones that have been deployed using externally owned accounts. The function selector approach needs to be improved a little bit more to see how applicable it is. So all the code that exists for it has been created in the last month, 4 weeks. So, you know, it does show a little bit of promise there, and maybe it could be improved and provide substantive gains. So if we could see, say, 25% improvement over the other techniques, then its increased complexity might be worthwhile because it might provide substantive gains to the witness size. At the moment, we've done our analyses. So that analysis, that graph you saw was only over 3,000 blocks. We've got another data set of several 100,000 blocks, but we really need to have overall 1 million blocks or so that we look at. So 9 to 10 million is essentially 2019 with, I think, a little bit of 2020 involved as well, but 1 million blocks would be a good number. So we need to include the multi-Merkle proofs into the evaluation as well. And it will be good, rather than using the approximation of the static code analysis, to actually use the code execution traces. And so actually see how much code is really used and then use that as the evaluation criteria, because that will tend to let the other approaches, strict, fixed and jump test, they may have advantages over the function selector in that if we use that. So that'll be interesting to see what effect that has. And for the function selector, rather for the jump test, fixed and strict, we need to try different chunking sizes to work out what's the optimal size. And I think all of the analyses thus far, both by us and by others, has been using hex retries. And so using binary tries would be very useful, because it may give different results. Well, it will give different results, and understanding exactly what the differences are is important. So in 2 weeks' time, Raghavendra is going to be back, and he's going to be talking about polynomial commitments. On the following Monday after that, we've got the Supply Chain on Blockchain conference, and you can register for the conference at that link. Registrations cost just Australian dollars 40. So it's quite a cheap conference. It's online, so you don't have any travel costs, and you don't have to worry about any travel restrictions. We're looking at having another talk 2 weeks after the polynomial commitment one. I'm just getting the speaker to lock in. That's likely to be in the afternoon because the person lives in Europe. On August the 5th, we've got Tim Biko. He's been one of the people driving the efforts around EIP 1559. And so he's going to talk about that EIP and escalators, and essentially how the Ethereum fee market might be tackled and changed. And so the Ethereum fee market is how you choose the gas price for a transaction. So because Tim lives in Canada, that's actually going to be at 9:30 a.m. rather than the typical 12:30. But it should be a good talk. And that is it. So are there any questions? Or have we left everyone speechless?
I was going to ask about the binary tries and stuff, but you said you're going to look at that in the future. So I think that the only thing you need to really analyze is the total byte size. So processing time is reasonable as well, but yeah, I don't think individual items is really, because if you're going to have some that are more, some that are less, and what really matters is what's the total. Yeah.
Well, that's the thing, though. But I think knowing the limits is important. So if someone could send an attack contract in and deploy a contract that could cause, if someone could send an attack contract in that could cause a node to spin for 5 seconds and go off the network, that'd be pretty big. We need to try and make sure that's not possible.
Yeah, I think my gut feeling is that the functional analysis, whilst it is good in terms of can get a better solution, I struggle to see how that's feasible to implement in code because it relies on being solidity. Right? What if it's Viper code, or what if it's whatever, and it's not a static code analysis is a very fluidy sort of thing compared to the fixed byte ones, which, or even the jump action would work because that's a fixed code. But
and
that's my gut feel.
Yeah, and that is everyone else's gut feel too, or a lot of other people's gut feel. That simple, not necessarily perfect, but simple trumps complicated but slightly better. So the question is, and I mean, the thing, to be honest, always honest, but telling you how it is, that graph that was produced between 11 p.m., 11 a.m. and 12:15 today. So in the hour or so before the talk, it's been a very interesting last week or so. Even with that graph just by itself, it shows there is maybe a 10, 20, 25% improvement. And I guess the question is, if you have real function traces, how does it compare? And the question as well is, how much of an improvement would it need to offer for people to say, hey, that is enough of an improvement that we're happy to wear the extra complexity? And that's a big question that, that could be political.
even the attack vectors you're talking about, in terms of if it's a fixed size, then there's not really many attack vectors, because you can max out at I touch every point in the 24K code, but that's what I'd have to send now anyway. So yeah, there's no the attack time is on would be on the analysis time.
So I have a question. There are techniques, not new ones, quite old, let's say more than 10 years ago, called the proof carrying code that enables you to, before a client, let's say, executes some code, they can check that the code they're going to execute is safe. So is it related to the problem you want to solve? And if it is, can you just borrow from these techniques, because the proof is built offline, and when you receive it, you just need to check it. And checking is usually easier and faster than running some static code analysis.
Yeah, the static code analysis, though, is used to split the code. So you're saying, could you give the split the code already Merkleized and have some proof that the Merkleized code matches reality? I have actually been, so I had not heard of the technique, but I had been thinking of that as a possible thing, which would then remove the requirement around needing to Merkleize on the Ethereum client when you're deploying. Yeah, so that's interesting that there is a technique. Not surprising.
So there's quite a lot of literature on the problems. If you Google proof carrying code, you'll find lots of pointers.
But one comment though, is proof carrying code about well, it's definitely about saying that the sent code is not tampered with, but it's not about optimizing the amount of code to be sent, right? The code Merklization or this whole code chunking strategies are about optimizing the amount of code that needs to be sent in tandem with having a proof that whatever the code is sent is correct. So I think that's where it differs in terms of proof carrying code.
I think with the one thing you could look at is also reverse the whole process. If you've got that fixed size chunking, say, for example, and when you're executing the code the first time, you're running through calculating every instruction, the gas cost, and working out what the result is to package that up to transmit it for everyone else to verify, right? And you only want to send the code that you actually executed. If there is a cost per chunk in the gas cost, which can be known in advance, obviously, because you know which code's going to, it's just like estimating any sort of gas. And that was optimized, then the compiler might actually build to optimize the code so that you don't have code. You then rely on, they go and update the Solidity compiler to actually optimize code to put it on, align it to the chunk boundaries.
Yeah, we've talked about this as a possibility too. It's funny though, I'm not sure. So you would, I would assume that they would want to do that, but yeah, I guess you would, once you have a pricing strategy declared in the Ethereum clients due to a hard fork, then then people will align based on that to produce the cheapest possible code. So what we then need to do is we need to make sure that the crypto economics is aligned with what's best for the Ethereum clients, because otherwise people will do something that isn't best for the Ethereum clients because it's cheaper.
Yeah, so you're then effectively trying to price or analyze a dynamic system, because if you implement system A, the behavior will change. So even though right now you might say, oh, functional ends up as 20% better, if you put in fixed and then they change the compiler, that might have just wiped out the benefit of trying to do functional analysis.
True, but as we could see from the diagram, the graph that Sandra put together, there's still an awful lot of old code, contracts that have been deployed long ago that are still executing, and you would assume that, you know, if you've got a Solidity compiler from, I don't know, a year and a half, 2 years ago, and so contracts from 2 years ago are still being executed, which, I mean, given the whole idea of Ethereum is the contracts are up there forever and then you can use them forever. So yeah, so you might find that there's a very, very long tail for contracts being used over time.
So I had another comment on the fact that you want to send, let's say, a reduced amount of code rather than all the code. So unless I'm missing something, and in this case, just let me know, it's equivalent, right, to detecting dead code in a program. If you can detect dead code, you don't need to send it. So if you could compute the minimum amount of code that you have to send across, you would be able to detect dead code in a program. And this problem is in general non-computable, non-decidable. You can't do that. So you will most certainly every time, as you say, end up with another approximation of the code that has to be sent. And in this case, something that's very important to actually evaluate is the sort of the benefit of your approach, because you're bound to have some over approximation. So what do you gain if you run your system? Or is it, I mean, are there boundaries such that whatever you do, you'll send 90% of the code? And in this case, that's not worth using it.
Yeah, and I think that is an analysis we need to do to try and understand how much, I mean, and that's why the actual function traces, actual execution traces would be so interesting, because that'll tell us the amount of unneeded code that's being sent.
But also in this case, if you try to, let's say, do a dry run to check what has to be sent across, you sort of assume that you can run the same code twice at different time, right? And you will get the same execution. So I don't know if this is true, because if some code is based on, you know, using a timestamp or the current wall clock, running it twice at different times could give different, or the price of Ether, for instance, it could give different executions. If
you're talking about, I think they're talking about within the context of one block. So within the context of this is the execution given this inputs of function X at this point. And obviously every Ethereum node has to validate, gets the same result as you, right? If the result of the calculation is transfer 10 Ether, then when everyone's going to process exactly the same code and get exactly the same result, it's got to be deterministic, because that's, yes, someone else might process that contract later. But I think this is within the context of one block, isn't it? Not the contract in general.
Yeah, but if you sort of save the, I mean, if you schedule the execution to be processed or executed later, you may not get the same trace.
But that would be a different block, a different, you know.
Yeah,
if you're saying,
okay.
yes, if you say send current time times 10 Ether to someone, then everyone has to execute that with the same value for current time for that transaction to be a valid transaction.
Okay.
Correct. Yeah, it's all got to have the same starting state. Yeah. All right. Golly, oh, sorry, there's another question. Sorry, go ahead.
I wanted to ask, so given that we are talking all the time about about static analysis, so why can't this be done in a dynamic way? Well, it's dynamic in the sense, okay, I think I already got my own answer.
Yeah, I mean, the big reason, so to answer a question that you might have been thinking of, which is, so why can't you just send exactly the code bytes that are executed? And that is, of course, because you need to be able to prove that those bytes that were executed were part of the contract. And the way you do that is because of the hashes linking to the code hash. And so, yeah, you can't know beforehand which code bytes are going to execute exactly. you can use something like the static code analysis to work out the bytes that might execute, or you can use the other techniques to monitor which bytes are executed and then just send blocks which happen to contain them. But actually trying to come up with a proof that just proves exactly which bytes were executed and that they're part of the contract is very hard.
I think, a step further. Is it correct to say that once we have the trace and the exact bytes that have been executed, we have to create the witness based on a structure, and that the static analysis prepares that structure, that template, let's say?
Well, the static analysis works out what goes into the leaves of the Merkle-Patricia trie for that approach. And the idea is that for that technique, you wouldn't actually worry about what the trace shows. You would only worry about the function selector, and because that would tell you which leaf to send, and all of the code that will execute should be within the leaf that's sent. The reason for having the trace is to compare the function selector approach with the other approaches, because the other approaches won't need to, say, send extra code, say if there's conditional logic.
I'll think about it.
So I can add one perspective to that. So the trace is a dynamic thing, which is like an artifact of a single transaction. But a code Merkle trie has to be constant for a period of time. So that has to be constructed at the deploy time, which needs to cater for all transactions. So at that time, you can only statically analyze the code because you don't know the contract states that it can possibly in future. So you can statically analyze the code and make some trie structure, either through function ID or fixed size, jump test, whatever it is. You make this trie structure. And when a transaction executes, let's say you have the trace, which actually shows the exact bytecodes that were executed. And based on that, you send the chunks that it fitted in. So the Merkle trie structure happens at the deploy time. That's why we need static analysis, can't rely on dynamic analysis.
After you have the execution, you send the chunks of the trie that was generated on the static analysis.
Yes.
Yeah, so that's what I meant with the template. Yeah, okay.
Yes.
Yeah, okay, thank you.
So just to make sure I understand well, you want to send somehow you have an execution trace and you want to send the footprint on the program that is used to generate this trace. Right? So if you have the full trace and it's a finite trace, you could as well just send the sequence of steps and opcodes that have to be used, right?
How do you verify in the
recipient? Yeah, no, I agree, but that's the same. How do you verify that the subset of the programs that you sent is the correct one?
Sorry, say that again.
You have to verify that if I sent you a subset
of
the program, right? I have to verify that this is the correct one.
Yeah.
So as a sort of a sub-problem, I would say if my program is a linear trace, I should be able to do it for a linear trace.
Yes.
If a program has no conditional logic or no loop and so on. So I could do it as well if I know what trace is going to be executed. I could collect the sequence of instructions that are going to be executed and send this program across without sending the footprint. Right? If I know that the loop is going to be executed 5 times, I could send the body of the loop 5 times as a program and say, I certify that this is what has to be executed.
Yeah, well,
certification is sent though at the contract deployment time. Here is the root proof of this code, and that's stamped into the block. I don't know what the future execution is going to be, so somehow you've got to link that future execution back to the original hash.
That's right. you deploy the contract, you've got the root, you've got the code hash, which is part of the state, the storage state. And then, so now I'm saying I've got a transaction and that's going to execute on that code. You're a stateless client, so you've got no state whatsoever. How can I prove to you that this is the code that needs to execute, or this code that I'm saying you should execute is part of this contract? And so how you do that is you send, say, you send the pieces of the Code Merkle-Patricia trie that then are part of the overall storage overall state trie, and say, well, here, these pieces are definitely part of the state trie, so you can say that they are valid code. So that's how you prove that the code is code that is part of that contract code. And then how you prove that you haven't executed off the boundary of the code you've been supplied, I think is something different again. I think there'll have to be some magic, you know, like opcode or, you know, indicator that, you know, you've just jumped to something that, you know, is completely, you know, you do not have. So if your Solidity, your bytecode does a jump and it jumps to, say, some code that hasn't been delivered as part of the witness, then there should be some error of some sort. People aren't talking about that so much because I think the assumption is that all of the code that needs to be delivered to execute will be delivered, and otherwise, you know, you wouldn't produce a block with an invalid transaction in it.
Or if it doesn't execute, then every other node will reject it. Is what Horatio said, that the problem is that the proof is done at one time before you know what's going to execute, and then later on you've got a definite trace of one specific execution, and how do you link them together?
And I can see that we should have had more introductory slides at the start to try and meld this into everyone's mind that this is the problem that we're dealing with. Yeah. Oh, well, next time we do a Code Merklization talk, we'll be all ready. All right, so we've gone 38 minutes overtime, which is probably a record. I didn't even notice. I was just presenting away, as I think was Raghavendra, and we've had a lot of questions, so it's all good. So thank you everyone for coming along.
Thank you.
Thank you.
Thanks a lot.
Bye.